Yeah, in this lecture we will discuss a theorem which tells us that the cardinality of any Li set in a vector space, if we have a vector space over the field F, then in this vector space the cardinality of Li set is always less than equal to the cardinality of any spanning set. If we take any Li set and if we take any spanning set, then cardinality of this set will always be less than equal to cardinality of this set. Okay, we will prove these theorems. Okay, so first we will assume, suppose u1 u2 dot dot um are linearly independent vectors. Okay, and w1 dot dot wn is spans v. Okay, so we have taken linearly independent vectors and this w1 to wn spans v. So to show, what is to show? To show m is less than equal to n, we have to show this m is less than equal to n. Okay, so we will do in some steps. So step first, okay, since w1 wn spans b, since it spans b and u1 belongs to v, this will imply there exists c1 dot dot to cn belongs to field such that we can write u1 as a linear combination of all these w's. So it will be c1 w1 plus dot dot cn wn. Okay, so since w1 w2 dot dot wn can span whole v and w1 is in v, so this can be written of this form. Okay, and since this is non-zero vector because this is linearly independent vector, one of the CIs should not equal to 0. Okay, so without loss of generality, assume c1 not equal to 0. Okay, since this is not equal to 0, so at least one of the CIs has to be not 0, because if all the CIs will be 0, their linear combination will also be 0, but this is not 0 vector. So we assume without loss of generality that c1 not equal to 0. So now if c1 not 0, we can write w1 c1 w1 equal to u1 minus c2 w2 plus dot dot cn wn. What we did here, that we subtract all these terms from second to nth and left c1 w1. So from here, if we find w1, what we will do, we subtract w1 to c2 w2 plus dot dot cn wn, and if we have to divide c1. Okay, c1 is non-zero, so we can divide by c1. So we got the value of w1 this. Okay, now I claim that, yeah, if we remove w1, okay, then if we remove w1 and add u1 in w1 dot dot to wn, then remaining set of length n, if we add u1 and remove w1, the length of the set will be only n, and including u1 also span v. Okay, so now we are going to remove w1 dot to wn. In this set we will remove this vector and add u1. Okay, so what we got, new set of vectors u1 dot dot to u1 w2 dot 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 wn. So we got new set of vectors. Now I claim that this also span v. Okay, now to show u1 dot dot wn spans v. Okay, since what we know that w1 dot 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 wn span v, it is given that all the w's is spans v, so we can write any vector v from v. Let v belongs to capital V. So this vector can be written as c1 w1 plus c2 w2 plus dot 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 cn wn. Okay, and the ci's are from the field for all I. Now since we okay, so I can write here alpha 1 alpha 2 because we have taken c1 c2 cn in previous linear combination, so we can take here alpha 1 w1 alpha 2 w2 plus alpha n wn. Now if we see here, w1 can be written as the linear combination of u1 and remaining w's w2 dot 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 wn. So we can put this value at the place of w1. So it will be what it will be, w1 minus c2 w2 plus dot 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 cn wn divided by c1. This is the value of w1 plus alpha 2 w2 plus dot 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 alpha n wn. So now if you observe this step, what it says, any vector can be written as linear combination of w2 to wn. Here w2 is used and wn is used. So any vector v from the vector space V can be written as the linear combination of u1 and w2 w3 dot 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 wn. So u1 dot w2 wn spans v. Okay, so we have proved here that if we remove w1 and add u1, then the resulting new set also spans v1. Okay, so now what we will do, we will add u2, and because of this is a spanning set, if we add u2, the new set will be linearly dependent, and in this process we will remove w2 without loss of generality. We will remove w2. So new vector u1 u2 w3 dot 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 wn also spans b. Okay, so whenever we have we add u1, we remove w. Whenever you add ui, we remove wj, sum of the value of j and some value of I. So whenever we add ui, we remove wj and we got again a spanning vector. Yeah, and why we can add or we can why we can remove, because of after removing we got an a spanning set also. So whenever we have uis, we have wj. If this if the condition holds that this is the spanning set or this is the li set, okay, so whenever we have ui, we have wj. So number of ui's, what will be number of ui is less than equal to number of wj. This will imply cardinality of linearly independent set is less than equal to cardinality of a spanning set, and this can be any linearly independent set or this can be any spanning set. Okay, thank you. If you have any queries, please ask in the comment box and also subscribe my channel. Thank you.